The year is 1993, Las Vegas. A 19-year-old kid walks into the staging lanes at the Las Vegas Motor Speedway with a beat-up Fox body Mustang that shouldn't even be there. The other racers, guys who've been building turbo cars since before this kid could drive, they're laughing. They've got $50,000 race cars, professional crews, sponsor money. This teenager? He's got a soldering iron, a Radio Shack receipt for $60 worth of parts, and an idea that's about to flip the entire turbocharger world upside down. What happens next isn't just a story about winning races. It's about how a Nevada street racer solved a problem that had plagued turbocharger technology for decades, a problem that million-dollar racing teams couldn't crack. He did it with electronic components you could buy at any electronics store, some basic understanding of pneumatics, and the kind of creative thinking that only comes from having no money, but needing to go fast anyway. This is the story of the electronic boost controller, a device so simple, so elegant, and so devastatingly effective that within 2 years, every serious turbo racer in America would be running one. But here's the kicker. The racing establishment fought it. They called it cheating. They tried to ban it. They did everything they could to stop it. Because when a teenager with $60 worth of parts starts beating cars worth more than most people's houses, the old guard gets nervous. To understand why this invention mattered, we need to talk about turbochargers in the early 90s. See, turbocharging wasn't new. Forced induction had been around since World War II fighter planes. By 1993, turbos were common in everything from Japanese imports to big block drag cars. But there was a fundamental problem that nobody had solved. Controlling boost pressure, the amount of compressed air a turbo forces into an engine, was crude, inconsistent, and incredibly frustrating. The traditional method was the wastegate. Think of it as a pressure relief valve. When boost pressure reaches a certain level, the wastegate opens, diverts exhaust gases away from the turbine, and prevents the turbo from making more boost. Simple concept. The execution? That's where things got messy. Wastegates were controlled by springs. Want more boost? Install a stiffer spring. Want less? Softer spring. But here's the problem. Springs don't care about track conditions. They don't adjust for temperature. They don't compensate for altitude. They just do what springs do. Compress and extend based on pressure. Period. Professional race teams would carry boxes of wastegate springs. Different tensions for different tracks. Crew chiefs would spend hours between rounds swapping springs, trying to dial in the perfect boost for the next run. And even then, it was a guess. Temperature changes between morning and afternoon, your boost changes. Track at sea level versus mile-high Denver, completely different boost characteristics. The spring that worked perfectly in qualifying might blow your engine in eliminations. It was madness. Enter our 19-year-old protagonist. Like most Nevada street racers, he couldn't afford the constant spring-swapping game. He was running a junkyard turbo on a 5.0 Ford that had already seen better days. But he understood something the establishment didn't. He understood that controlling boost wasn't about mechanical force. It was about controlling information, specifically the pressure signal that told the wastegate when to open. The wastegate actuator works on a simple principle. It's a diaphragm connected to a rod that opens the wastegate valve. Pressurized air from the compressor outlet pushes against this diaphragm. When the pressure overcomes the spring tension, the rod moves, the wastegate opens. Boost stops climbing. The breakthrough came when our young racer realized you didn't need to change the spring. You just needed to lie to the actuator about how much boost was actually being made. His solution was brilliant in its simplicity. He installed a solenoid valve, basically an electrically controlled air valve, between the boost source and the wastegate actuator. This solenoid could bleed off pressure before it reached the actuator. If the turbo was making 15 psi but the solenoid was bleeding off 5 psi. The actuator only saw 10 psi. It wouldn't open until the actual boost hit 20 psi. By controlling how much pressure the solenoid bled off, you could control exactly when the wastegate opened. And here's the beautiful part. You could control the solenoid electronically. No spring swapping, no mechanical adjustments. Just turn a knob. The first prototype was laughably crude. A 12-volt solenoid from an old carburetor, some vacuum hose, a potentiometer from Radio Shack to control duty cycle, a few resistors and capacitors to smooth out the signal. Total cost? $60. Maybe $70 if you bought new hose. The entire circuit fit in a small project box that could mount anywhere in the engine bay. Installation took 20 minutes. Tuning took seconds. But crude didn't mean ineffective. That first electronic boost controller transformed the Fox body Mustang from a 10-second car to a 9-second car overnight. Same engine, same turbo. Just precise, repeatable, adjustable boost control. The kid could dial in 12 psi for the burnout, 18 psi for first and second gear, then ramp up to 25 psi for the top end. Different boost curves for different parts of the track, something that was literally impossible with mechanical wastegate springs. The local racing community's reaction was immediate and hostile. At first, nobody believed it. A $60 box outperforming $1,000 wastegate setups? Impossible. Then came the accusations of cheating. He must be hiding nitrous, running illegal fuel. Something, anything other than admitting this teenager had outsmarted them with basic electronics. Tech inspectors tore his car apart. After every win, they found nothing but wires, a solenoid, and a small black box that looked like it belonged in a science fair project, not a race car. The real controversy started when he began beating sponsored cars. We're talking about professional teams with factory support, unlimited budgets, and decades of combined experience. They'd show up with trailers full of spare parts, crews of mechanics, and engines built by the best shops in the country. And they'd lose. To a kid who worked at a muffler shop during the week and built his boost controller on his mom's kitchen table. The turning point came at the Streetcar Super Nationals in November 1993. This wasn't some local grudge race. This was the biggest small tire race in the country. 300 of the fastest street cars in America. Fox body Mustangs running single turbos, twin turbo Camaros, big block nitrous cars. The kid shouldn't have made it past the second round. Instead, he went to the finals. His opponent was a legend. A guy who'd been racing turbo cars since the 70s. His Buick Grand National was a work of art. Precision turbo 76mm turbocharger, Motec engine management, custom fabricated everything. The car had run 8.90s consistently all day. The smart money was on the Buick. The kid's Mustang had struggled with traction, running anywhere from 910s to 930s, depending on the pass. But that's where the boost controller changed everything. Between the semifinals and finals, track temperature had dropped 15 degrees. The Buick team scrambled to adjust. They swapped wastegate springs, changed timing, adjusted fuel curves. They had 30 minutes to completely recalibrate for the cooler, denser air. The kid? He turned a knob 3 clicks to the left, dropped boost by 2 psi to account for the extra oxygen in the cooler air. Took him 10 seconds. The Christmas tree dropped. Both cars launched hard. The Buick pulled ahead by half a car length through first gear. But something was wrong. The turbo was making too much boost in the cooler air. You could hear it in the engine note. That sharp, angry sound of detonation. The driver had to lift. Meanwhile, the Mustang hooked and went. 9 flat at 151 miles per hour. The kid had just won the biggest race of his life with a $60 boost controller. But the story doesn't end there. Within a month, every turbo racer in Vegas wanted one of these magic boxes. The kid started building them in his garage. 20 controllers the first month, 50 the next. By spring of 1994, he was shipping them nationwide. The design evolved rapidly. Version 2 added multiple boost settings you could switch between with a toggle. Version 3 integrated a pressure sensor for closed-loop control. The solenoid would actively maintain exact boost pressure regardless of atmospheric conditions. The technical evolution was fascinating. The original solenoid valve was a simple on-off design, pulsing at about 30 Hz. This created boost spikes and inconsistent control. The second generation used a proportional solenoid that could vary flow continuously. Instead of bleeding all or nothing, it could bleed exactly the right amount of pressure to maintain perfect boost. The control circuit grew more sophisticated too. Microprocessors replaced analog timers. LCD displays showed real-time boost pressure. Some versions even had data logging capability. By 1995, professional race teams couldn't ignore it anymore. AMS Performance, one of the biggest names in import racing, developed their own electronic boost controller. HKS in Japan released the EVC. Greddy came out with the Profec. Suddenly, every major turbo manufacturer was scrambling to develop electronic boost control. The technology the establishment had rejected was now industry standard. But here's the thing, they were all just copying what a teenager invented in his garage for $60. The impact on motorsports was immediate and profound. Turbo drag cars that had been limited to running consistent boost suddenly had infinite adjustability. Rally cars could change boost maps for different stages. Street racers could run low boost for daily driving, then crank it up for race night. The electronic boost controller didn't just control boost, it made turbocharging practical for everyone. But let's get into the real technical meat of how these things worked. Because the engineering, while simple in concept, was genius in execution. The solenoid valve at the heart of the system operated on pulse width modulation. Think of it like a very fast finger tapping a hole. The faster you tap, the less air escapes. By controlling the duty cycle, the percentage of time the solenoid was open versus closed, you controlled exactly how much pressure reached the wastegate actuator. At 0% duty cycle, the solenoid was fully closed. All boost pressure reached the actuator, and the wastegate opened at spring pressure. At 50% duty cycle, the solenoid was bleeding half the pressure, so the wastegate wouldn't open until boost was double the spring setting. At maximum duty cycle, almost no pressure reached the actuator, and boost would climb until mechanical limits or engine destruction, whichever came first. The control algorithm was equally clever. Early units used simple open-loop control. You set a duty cycle, and that was it. But this had problems. As boost increased, the pressure differential across the solenoid changed, altering flow rates. The kid's solution was to add a feedback loop. A pressure sensor monitored actual boost pressure and adjusted solenoid duty cycle in real time to maintain the target. If boost was too low, decrease bleed. Too high, increase bleed. Simple PID control that any engineering student would recognize, but revolutionary in 1993 racing. The mechanical installation was intentionally simple. 3 vacuum lines, 2 wires, and a boost source. The solenoid went inline between the compressor outlet and wastegate actuator. Power came from any switched 12-volt source. Ground to chassis, that's it. No special tools, no tuning software, no laptop required. This accessibility was key to its adoption. Any racer with basic mechanical skills could install one in under an hour. Performance gains were staggering. Cars that had been struggling to make consistent power suddenly became weapons. A typical turbo drag car in 1993 might see boost variance of plus or minus 3 psi between runs. With electronic control, variance dropped to plus or minus 0.2 psi. That consistency translated directly to elapsed times. Cars that had been running different times all day suddenly became predictable. Bracket racers loved it. Heads-up racers feared it. The most impressive demonstration came from a shop in Texas that did back-to-back dyno testing. Same car, same day, same temperature. With mechanical wastegate control, the car made between 680 and 720 horsepower across 5 pulls. Boost varied from 18 to 22 psi depending on how fast the turbo spooled. With electronic boost control set at 20 psi, the same car made 710 horsepower. Every pull, 5 runs, all within 3 horsepower of each other. That's the difference between winning and losing. The racing establishment's resistance was fierce, but futile. NHRA initially tried to ban electronic boost controllers in stock and super stock classes. Their argument was that it provided an unfair advantage. The irony was rich. A $60 device was considered more advantageous than tens of thousands in engine development. The ban lasted 1 season. By 1995, electronic boost control was specifically allowed in all but the most restrictive classes. The street racing scene embraced it immediately. No sanctioning bodies meant no rules against innovation. Plus, street racers needed adjustability more than anyone. Racing at different locations, different altitudes, different weather conditions, mechanical control was a nightmare. Electronic control meant you could dial in perfect boost whether you were racing at sea level in Florida or mile high in Colorado. Just adjust the knob and go. Import racers were the most enthusiastic adopters. The Honda crowd discovered you could run massive turbos with electronic boost control. Previously, big turbos meant laggy, peaky power bands that were impossible to drive. With electronic control, you could run low boost down low for response, then ramp up boost as RPMs climbed. Suddenly, small displacement engines were making 4-digit horsepower. The kid's invention had inadvertently launched the import performance revolution. The technical advantages went beyond just adjustability. Electronic control eliminated boost creep, where boost would slowly climb as exhaust temperature increased. It prevented boost spikes during gear changes. It allowed for overboost protection, cutting boost if pressure exceeded safe limits. Some advanced units even had gear-based boost control, allowing different boost levels in each gear for optimal traction. But perhaps the biggest impact was democratization. Before electronic boost control, consistent turbo performance required extensive knowledge and experience. You needed to understand spring rates, actuator preload, temperature compensation. With electronic control, anyone could achieve professional-level boost control. Turn a knob, watch the gauge, make power. It removed the black magic from turbocharging. The kid who started it all? He sold his company in 1996 for a number that's never been publicly disclosed, but insiders say it was 7 figures. Not bad for a 19-year-old with a $60 idea. He stayed in the industry, consulting for major manufacturers and developing new technologies. But nothing he did afterward had the same impact as that first crude boost controller built on a kitchen table. The legacy is everywhere. Every modern turbocharged car, from economy cars to supercars, uses electronic boost control. The 2024 Porsche 911 Turbo's sophisticated boost management system? Same fundamental concept as that $60 box. The Ford F-150 EcoBoost's altitude compensation, direct descendant of the kid's invention. Modern Formula One cars with their complex hybrid turbo systems. They're using the same pressure bleed principle, just with fancier solenoids. The aftermarket hasn't forgotten either. Companies like TurboSmart, Grimspeed, and Hallman still sell electronic boost controllers based on the original design. They're prettier now, with billet aluminum housings and full-color displays. But inside, same solenoid, same bleed principle, same brilliant simplicity. Prices have gone up, though. What cost $60 in 1993, parts now sells for $300 to $500 retail. Progress, I guess. The technical specifications of modern units are impressive. Response time under 10 milliseconds. Boost control accuracy within 0.1 psi, multiple boost maps, launch control integration, scramble boost functions. But strip away the features, and it's still just controlling when a wastegate opens by manipulating pressure signals. The fundamental innovation hasn't changed because it doesn't need to. The kid got it right the first time. What made this invention special wasn't just the technology, it was the timing. The early 90s were the perfect storm for turbo innovation. Affordable turbo kits were becoming common. Engine management systems were getting sophisticated enough to handle boost. The Fast and Furious culture was brewing, even if the movies hadn't hit yet. Into this environment dropped a device that made turbocharging accessible, adjustable, and reliable. It was exactly what the market needed, exactly when it needed it. The story also highlights something important about innovation. The best ideas don't always come from established players with unlimited R&D budgets. Sometimes they come from teenagers who can't afford the conventional solution, so they invent something better. The racing establishment had accepted wastegate springs as the only solution because that's how it had always been done. It took an outsider with nothing to lose to question that assumption. Consider the scope of the change. In 1992, controlling turbo boost meant mechanical springs, constant adjustments, and accepting inconsistency as part of the game. By 1995, electronic boost control was mandatory equipment for any serious turbo build. That's 3 years from garage invention to industry standard. In the conservative world of motorsports, that's lightning speed. It speaks to how desperately the technology was needed. The financial impact was enormous. The performance aftermarket for electronic boost controllers is now worth hundreds of millions annually. Every turbo kit sold includes some form of electronic control. OEM manufacturers spend billions developing sophisticated boost control strategies. All of it traces back to a teenager who thought there had to be a better way than swapping springs in a parking lot. But the real legacy isn't financial. It's the cars it enabled, the 1,000-horsepower street cars that dominate today's racing scene. The 2-liter 4-cylinders making more power than yesterday's big blocks. The diesel trucks running 40 pounds of boost and towing 20,000 pounds. None of it would be practical without precise electronic boost control. That $60 box didn't just control pressure, it unleashed potential. The critics eventually admitted defeat. The same tech inspectors who tore apart the kid's car looking for cheating were running electronic boost controllers on their own cars within a year. The professional teams that complained about unfair advantages were first in line to buy the technology. Even the NHRA, after trying to ban it, now requires electronic boost control in certain turbocharged classes for safety reasons. Modern racing would be unrecognizable without this invention. Imagine pro-mod cars trying to manage 3,000 horsepower with mechanical wastegates. Picture World Rally. Championship cars attempting to adjust boost for different stages using springs. Think about time attack cars trying to balance boost for different corners mechanically. It would be chaos. Electronic boost control isn't just convenient. At modern power levels, it's essential. The sophistication has grown exponentially. Today's controllers can interface with engine management systems, traction control, launch control, and even GPS to adjust boost based on location on track. Some units learn and adapt, building boost maps based on previous runs. Others can be adjusted remotely via smartphone. But at their core, they're still doing what that first $60 box did, lying to a wastegate about how much boost is being made. The engineering principles have influenced other industries too. The same pressure bleed concept is used in industrial pneumatic controls, HVAC systems, even medical devices. The idea of using electronic control to manipulate mechanical pneumatic systems opened doors in fields far removed from racing. That 19-year-old didn't just revolutionize turbocharging, he demonstrated a new way to think about pressure control. Looking back, it's amazing this took until 1993 to happen. All the components existed. Solenoids had been around for decades. Electronic control circuits were common. Turbos had been using wastegates since the 50s. But nobody connected the dots until a teenager with more ambition than money needed to go faster. It's a reminder that innovation isn't always about inventing new technologies. Sometimes it's about combining existing technologies in ways nobody thought to try. The story resonates because it's fundamentally American. A young guy with an idea takes on the establishment and wins. No credentials, no backing, no permission. Just ingenuity, determination, and a soldering iron. He didn't set out to revolutionize an industry. He just wanted to win races. But by solving his own problem, he solved everyone's problem. That's how the best innovations happen. Today, when you see a turbo car launching hard at the Strip, remember that the technology making it possible started in a Nevada garage. When a modern sports car seamlessly manages boost across its entire RPM range, that's the legacy of a $60 Radio Shack build. When import tuners make 4-digit horsepower from 4 cylinders, they're standing on the shoulders of a 19-year-old who refused to accept that springs were the only answer. The electronic boost controller is one of those rare inventions that seems obvious in hindsight, but required genuine genius to conceive. It solved a problem so fundamental that we now take the solution for granted. Every turbocharged vehicle on Earth uses some variation of this technology. From economy cars to hypercars, from diesel trucks to top fuel dragsters, they all control boost electronically. Because one teenager proved that $60 worth of parts could outsmart millions of dollars worth of tradition. What's the lesson here? Maybe it's that innovation doesn't require permission. Maybe it's that the best solutions are often the simplest. Or maybe it's just that when you give a creative mind a problem and very little money, magic happens. Either way, the next time you see a turbocharged car, remember the kid who changed everything with a solenoid, some wire, and the audacity to think differently. Think that $60 boost controller was impressive? Drop a comment about the most ingenious low-budget racing innovation you've ever seen. And if you want more stories about garage inventors who change motorsports forever, make sure you're subscribed. Because this kid wasn't the only one who outsmarted the establishment with hardware store parts and brilliant engineering.